Hello, welcome to Expressing Einstein Notation as Matrices. This is just one of many essays and articles on the Spoon-Fed Relativity website. You'll see some of the articles have been archived, so if you come out here to look at them, you will want to click on one that is not an archive. But currently I have an original and a part 2 and a part 3 and a part 4, all with their dates on them. Now, if we go to Einstein notation as matrices and come down to the bottom, you'll find that there is a Facebook comment section for each of these documents. And today I got my first question from George Cervinka. Actually, I have talked to him on the phone, so I got some clarification on this question. He asked if both of us were taking for granted that m equals n equals an identical number of dimensions, and yes, we are. If we have a two-dimensional coordinate system, then we might have x comma y in one coordinate system and r comma theta in the other coordinate system. And if we have an x comma y comma z, that might go to an r theta phi or something like that. Also, m and n might be the same coordinate system. M might represent x comma y comma z. N also might represent x comma y comma z. But there is no situation wherein the number of dimensions in the two frames of reference under consideration are not identical, because if there were, these matrix multiplications would definitely not work. I wanted to show a couple of examples of the use of Einstein notation kind of in a video form. There can use a little bit of clarification through the use of the video. In particular, we're going to be looking at this sort of equation here and exactly what this represents matrix-wise. This del phi del xy n direction, I'm going to write an n right arrow. The n is actually just referring to when n is 1, we put an x, del phi del x. And then when n is 2, we put a y, del phi del y. And then we will have the other matrix going down, and so we will also have an n arrow down here, and the dx dy, and that is equal to d phi equals that. And you can see really with standard matrix multiplication, the n is superfluous. It is kind of important to have it there to in the Einstein notation, because it describes the fact that those two things are equal tells you that it is an inner product. Let's say we had an expression that said del phi del x sub n down arrow, and we'll make that a different variable here to indicate that it's different, and then dx comma y, and then we're going to make a different thing here. We'll make it n right arrow. This would represent an outer product, del phi del x, this coming down. Well, this one's going to be coming down, so it's del phi del x, del phi del y. I should have written an x comma y there. And then this is going to be dx dy. And so this, when we multiply this one out, we're going to get del phi del x dx plus del phi del y dy. So this is just one term. On the other hand, this one is going to give us a 2 by 2 tensor, a rank 2 tensor, del phi del x dx del phi del y dy del phi del y dx and del phi del y dy. Now I don't know if this really represents anything in particular, but you can see that if you wanted to take this, if you wanted to take something like this and get this, you could take something I'm calling the sum of products, which I have been indicating as a capital sigma with a square around it, times 0, the identity matrix. So this this term over here would pick out, you would write this as sum of products with the identity matrix, with the, what is it called? Kronecker delta function, mn. And so you could actually pick out this term plus this term times 1 plus this term times 1. And I've been writing that way. And then what needs to be done there is these two arrows. When you're doing sum of products, you want this arrow to match that arrow and this arrow to match that arrow. So that's the sum of products notation. Okay, now let's look at this equation, which produces a rank 4 tensor. First of all, you can tell if this was written in Einstein notation, or the way that it's written in Einstein Field Equations for beginners, this would be del y, what is it, del y sub m superscript m del x superscript r del y superscript n del x superscript s. Now that is enough right there to distinguish what the form is, and it doesn't really attach itself to a particular format on the page. But what I've done is kind of restricted it to a particular form on the page, and I think it's a good restriction. It's just one that makes the matrix multiplication fairly convenient. So what's going on here? You'll see we've got an arrow and a double arrow. This arrow is associated with this arrow here. The double arrow is associated with these arrows here. Then we have a single arrow associated with this single arrow over here, and a double arrow associated with these two double arrows here. So how do you get from this little thing to this big thing? First of all, the r and theta variables are associated with the big arrow, and this is the external one. So you see the r and the theta go r, theta, theta. So the r is associated with the top, when m equals 1 up here, and the theta is associated with m equals 2 down here. And the r has x and y, and so the x is associated with the top one here, where r equals 1. When r equals 1, we get x, and the y is associated with when the bottom one is, or I'm sorry, yeah, the y is associated with r equals 2. When r equals 2, we put a y. So let me just practice that once more with, say, a PQ, del PQ del x, y, and we'll put a down arrow here and a double down arrow here. Really, for this purposes, we don't, the letter is superfluous once we figure out that it goes this way. It's a dummy variable. It doesn't really do anything. So let's just kind of go through it again, the way I would kind of run through it. Del p, we go del p over, and then del q, over, and we've taken care of the single arrow. And then we're going to do the double arrow, which is going to be del x, del y, and then del x, del y. Same thing with the other metric. We'll have, say, del p comma q right arrow over del x comma y double right arrow, and that is going to be equal to pretty extended matrix. It'll be externally, I'm going to have to move over so I can capture the whole thing. Del p will have del p, parentheses, and then del q in the first set, and then on the bottom we'll have del x, del y, and del x, del y. And then that all makes it very convenient for multiplying these things out, because it's regular matrix multiplication after that. Del r del x times del r del x is del r squared del x squared. Del r del x times del r del y is del r del x times del r del y. Del r del x times del theta del x is del r del x times del theta del x. Del r del x times del theta del y is del r del x times del theta del y. You repeat that all the way down with each thing having del r del y. You see a del r del y, del r del y, del r del y, del r del y times del r, and then this say del r del y here goes down this way. Del r del y, del r del y, del r del y, del r del y. Hey, just for fun, let's find the metric tensor for flat space. What I'm going to do is use del x comma y, del r comma s, no, del x comma y, and we're going to go down arrow, double down arrow, and del x comma y right arrow, del x comma y double right arrow, and we're going to come up with the metric tensor for flat space, which would be we'll just kind of run through. So we'll have del x over, del x over, del x over, and del x over. Del y will be on the bottom, del x, del y, del x, del y. I have a bad feeling about this. Okay, this is supposed to be y. I am sorry. Okay, so it's del x, and we can actually work this out. The differential of x with respect to x, partial derivative is 1. This is 0. The partial derivative of y with respect to x is 0, and del y is 1. So this is that thing, and this thing is just going to be the transpose of this. So I'm just going to write out 1, 0, 0, 1. Okay, and then I'm going to multiply that all out. So we will get a rank 2 tensor, and I have worked this out before, so I know what I'm going to get. 1 times 1 is 1. 1 times 0 is 0. 0 times 1 is 0, and 1 times 1 is 1. So that is 0, 1, 0, 0, 1. Then the second row is 0 times everything is just going to be 0, 0, 0, 0. The next row is 0 times 1, all zeros again. And the last row is 1, 0, 0, 1. So this is the metric tensor for flat space, and we're going to multiply that by delta mn. So if this is m coming down this way and this is n coming across this way, we're going to multiply that by, we're going to do a sum of products with 1, 0, 0, 1. And in this situation, we're going to have 1 times this. We'll have 1 times 1, 0, 0, 0, which is 1, 0, 0, 0, plus 0 times this one, plus 0 times this one, plus 1 times this one, 0, 0, 0, 1, and that gives you 1, 0, 0, 1, which is delta rs, or it's g sub rs, actually, to be multiplied by something else. Anyway, that is the metric tensor for flat space. So thank you for your question, George, and thank you for watching.